It's my turn again.
Any other questions on the stuff I presented? Okay, thanks.
All right, so as you all probably know, we've been investing heavily in sort of GPU computing. And I guess this part of the talk is to basically explore and provide you with examples of how compute is increasingly important to gaming and applicable in a lot of different settings. Okay, and I think that it's a very important trend to understand. I mean, in addition to rendering, I mean, GPUs are clearly not just for rendering, and games are no longer just about rendering. They're becoming increasingly sophisticated in terms of modeling the reality of the world, whether it's physics, whether it's AI behavior, lots of different things. In terms of GF100, we made a number of different improvements to the design to improve the performance of compute. And we're really, I mean, part of the goal of that, obviously, is to bring more uses, really, users and uses of the GPU, and bring more work to the GPU, where it's actually probably, arguably, much more efficient and much more appropriate. You'll be seeing some other talks later today about sort of the developer support in terms of C++ and also kind of debugging environments and so forth. All right, so in terms of compute, we're, in the earlier slides, we weren't incredibly crisp about the different ways that you get at compute in the GPU. And the reality is that there are a lot of different ways of doing it. We have, from NVIDIA, we've got CUDA and CUDA C++, because basically we did that development because it predated anything else that was out there in the world, and we continue to invest in it heavily because it's an extremely effective way of accessing the GPU. That said, we're enthusiastic supporters and collaborators on the design of OpenCL. I spent the better part of a year and a half working with folks at Apple on the design of OpenCL. The same can be said of direct compute, obviously for Microsoft. And then we've also working on toolkits for doing physics and ray tracing that allow developers to leverage those technologies through a higher level interface that makes it just a little bit easier for people to bring compute to bear in a game. So what kinds of things do people use this stuff for? And what's appropriate, what's emerging? There's some, in some sense, sort of obvious things. Histograms show up if you want to do tone mapping. You've got done HDR rendering, and you need to map it down for maybe a non-HDR display. HDR displays are starting to show up, but so you use them for that. There's convolutions. You have depth of field effects, which is sort of what you see here, where the foreground is in focus, and in the distance things are blurred appropriately with blooms around lights and so forth. Blurs. There's also, there are elements of realism that you'll hear more, again, you'll hear a bit more about today, but bringing physics to bear, making the world behave more like it should. And now the water, unfortunately, didn't have the physics, so it didn't look like any water you'd ever seen before, albeit it looked wet. So I mean, it's interesting because that's actually a really good demonstration of the need. But there's also, using simulation to do AI, to do animation, and then there's also AI. We'll talk a little bit about how it can be brought to bear there. Also, there's a variety of hybrid rendering approaches that compute is really appropriate for, and I'll walk through a couple of examples, not covering everything that's listed there, but we'll talk about those too. Any questions about sort of this general theme? All right, so this is, let's see, how this got obscured. I don't think that's on the slide. Is it me? Okay, great. Anyway, fine. So this is an effect in an upcoming game, Metro 2033. Can you, someone who actually knows something about this, say more details about, not what the effect is, but just sort of the details of the release of the game, things like that, or is that public knowledge?
It's announced.
It's based.
Okay, maybe you can tell us.
It's literally in a metro station based on the ground. There's been some nuclear explosion above ground and everyone's living underground.
Oh, cool. Okay.
Yeah, actually, it is a cult classic novel written, based in Moscow by Russians. It's very famous. Very Russian.
Oh, okay. All right. So this is another example of the depth of field, and actually, the projector doesn't do it justice. And if you want to, we should look at it on an LCD screen, just because it's beautiful fidelity, and it's just like, this looks like a photograph. There's a palette here, and it looks great, and things blur off in this. It's very realistic. Turns out that the depth of field effect that's used there is very computationally intensive. People have tried using pixel shaders, and you end up with something that is either dramatically too slow or just not possible, and it looks awful. If you look at the kind of techniques that Pixar has historically used to implement depth of field, you can't do it efficiently in the pixel shader because there's no shared memory. But you could bring direct compute to bear on this, and I won't attempt to describe how the problem is posed, but basically direct compute is used to solve a big linear system, a linear system of equations, and you iterate that linear system of equations in order to arrive at the quality rendering you see here. Okay, so we've invested fairly heavily in developing ray tracing technology and also improving the performance of our architecture for doing ray tracing. What we see here down at the bottom is a scene that's conventionally rendered, in the sense that it's rendered with a rasterizer. But then ray tracing is used to create realistic reflections and accurate shadows. So this is an example of a trend that I think we'll see more and more, that people are starting to call hybrid rendering, where you use a variety of techniques to produce an image. This is something, again, where in some sense the industry is taking the cue from the film industry. Sort of the GPU industry and the gaming industry is taking a cue from the film industry. Cars, for example, made very, very heavy use of ray tracing, which was not historically the case in the past, but it enabled them to produce a different variety of effects. So they have, cars was sort of this hybrid of conventional rays rendering and ray tracing. And you're seeing the same ideas being brought to bear in the GPU world, and sort of using compute enables that kind of thing. This picture on the right is, quote unquote, just a really nice rendering of a car. This is using some ray tracing technology. You're getting a demo later on today of that.
Next.
Oh, next. We're doing that now. Sorry.
It's going to be an exciting demo.
It's going to be an exciting demo. Okay. I hope it's not too exciting. Exciting isn't always, and I think that we should go look at that now. Yeah, sorry, I forgot to put a note on here saying that we're going to break and have a look at this. So, with that preamble, albeit a little clumsy, let's have a look.